All right, so we ended with this FRQ doing the calculation of delta T, or the change in temperature, which was an increase in temperature. And that was, we were doing like Hess's law, the shortcut way, which was products minus reactants with formation values. So now we're going to make our own Hess's law, which sounds kind of complicated, but I promise it's not that complicated. So instead of you being given the equations, what they can do is they can say, use this data below to calculate the enthalpy of formation of propane. So you go, okay, well, what is enthalpy of formation of propane? So remember, formation equations are the formation of, so propane is C3H8 from its elements, which would be carbon and hydrogen. Remember, hydrogen exists as a diatomic under standard conditions. So we have 3 carbons and 4 hydrogens, and we want to calculate this guy's delta H. Specifically, it's a delta H of formation. And you're going to do it using these values. So you go, okay, well, this is this guy's value, but I need to write a formation equation for it. So what's the formation of carbon dioxide? Well, you're forming carbon dioxide from its elements, which are carbon and oxygen, right? And this guy's delta H is negative 393 kilojoules per mole. And then you go, okay, so this is my formation equation, and this is the heat associated with it, or enthalpy. And then this is a delta HF of water. So this is the energy associated with forming water. So we're going to form water. Again, formation equations are the formation of a compound from its elements, and both those elements under standard conditions are diatomic. Now remember, when we write formation equations, you can only make 1 mole of the product. So this would require us to have a 1/2 here, right? 1/2 times 2 is 1. And this guy's delta H is given. Delta H is negative 285 kilojoules per mole. And now this is a delta H of combustion, meaning this is not a formation equation. This would say delta HF if it was a formation. So this is a combustion reaction. So we're going to write out the combustion reaction. C3H8 plus O2, right? Combustion makes CO2 and H2O. And the delta H of that is negative 2217. Okay, so you go, so what do I do? Well, you've just written your own equations on your own. They weren't given this time. And so now we're going to manipulate these 3 different equations to make them look like this one. All right, so first things first, I need 3 carbons. So I'm going to multiply that top equation by 3. 3, 3, 3. And then you have to multiply the delta H by 3, right? Okay, 3 carbons, check. I need 4 hydrogens. All right, so I'm going to multiply this next equation by 4. So 4. What's 4 times 1/2? It's 4 halves, right? Which is 2. Everything gets multiplied by 4. Okay, check. All right, makes propane. So I have propane, but it's on the wrong side of the reaction arrow. So I'm going to flip this. Flip it. So all of my reactants are now products, and all of my products are now reactants. Now when you flip it, you have to flip the sign. So this is now positive. And now I'm going to erase this one, this equation, because I just don't want it to confuse me. Okay, so let's see. I have 3 carbons, I have 4 hydrogens, 3 carbons, 4 hydrogens, and I have propane. We're going to kind of cross our fingers that everything else goes bye-bye. So look at. I'm having a brain fart right now. Give me 1 second. I didn't balance my propane equation. That's why. Okay, I'm sorry. I forgot to balance this. This has to be balanced. So there should be a 3 here for 3 carbons. There should be a 4 here for 8 hydrogens. And then that's 3 times 2 is 6, plus 4 is 10, so there's a 5 here. Sorry, I forgot to balance that. This is the balanced equation. Okay? All right, now let's look at everything that cancels. So 3 carbon dioxide on the products, 3 carbon dioxide on the reactants, cancels. 4 water as a product, 4 waters as a reactant, cancel. 3 oxygens plus 2 more oxygens as reactants is a total of 5 oxygens as reactants, and there's 5 oxygens as product. They cancel, and everything that's left is everything in my equation. So I'm going to give you a second to make sure you can calculate all of this. So it's 3 times negative 393 plus 4 times negative 285 plus 2217. So I'm going to give you a moment to make sure you calculate it. Again, we've been having, kids have been having a lot of calculator issues this week, so I know it seems like this is simple enough, but I really would like you to practice with your calculators with this. There's a lot of numbers, and it's easy to just like punch something in incorrectly. So I'm going to give about a minute for you guys to calculate it. So we should get the delta H to be negative 102 kilojoules per mole. So that is the enthalpy of formation of propane. So when you form propane from its element, this much enthalpy or heat is released per mole. Okay? All right, let's keep going. I'm going to skip this. You guys can do this on your own, but for the sake of time, I'm going to skip this. This is just practice. And the main thing, well, we're going to do 2 things today, but this is one of the biggest things. So this is we're going to be calculating delta H with bond enthalpies. And so just kind of as a prelude, in order to break bonds, you have to put in energy. Think about it. If you have to rip things apart, you have to put in energy. So breaking bonds is an endothermic process. And then when the new bonds are formed, that energy is now released. They're equal and opposite processes. And so the formation of bonds is exothermic. Now, let's say a hydrogen-hydrogen bond, okay, requires 436 kilojoules per mole of heat to be broken. That would mean that the same number of heat or same amount of heat is released when the new hydrogen-hydrogen bond is formed. So like they're just the same number but opposite processes. So bond dissociation energy or bond enthalpy. So an overall endothermic reaction is if you need way more energy to break the bonds than you get out of making new bonds, an overall absorption of energy happens. And if the reaction is absorbing energy from the surroundings, it will feel cold to us because all the heat is going into the reaction away from us. Remember when we do a lab and we take the temperature, we're always taking the temperature of the surroundings, okay? So what does exothermic mean for bonds? Well, if more energy is released from the formation of bonds than you had to put in to break the bonds, then the overall process is exothermic. Well, now if heat is released to the surroundings, it will feel hot to us. So the way that we calculate delta H using bond enthalpies by definition is bonds broken minus bonds formed, okay? Now, this is where it can get kind of tricky because when we calculated delta H using enthalpies of formation, which is what we were doing before, we did products minus reactants. This is when we use enthalpies of formation values. Now, this is kind of tricky, right? In a chemical reaction, whose bonds do you break? Bonds broken, right? Do you break reactant bonds or do you break product bonds? Anybody? Reactant, right? You're going in and ripping reactants apart. And what bonds are being formed? Your new bonds are your products. So it gets confusing because this is actually the reverse process in terms of our delta H when we used HF values was products minus reactants. This one's actually flipped. So instead of thinking of this as like reactants and products, I prefer, and I think the easier way to do it is to consider it bonds broken minus bonds formed. all right? Hopefully that will help with some confusion mathematically of which one gets subtracted from which one. So again, if you have more energy in your bonds at the end of the reaction than you did in the beginning, the process is endothermic. If more energy is released by forming new bonds than it took to break the bonds, then that process is exothermic. So before we start doing real calculations, let's talk about it conceptually. You take butane, you combust it, and you get carbon dioxide and water. Okay, so it says it's thermodynamically favorable. We'll talk more about that later. That just means that the reaction should happen at 25 degrees Celsius. And all the reactants and products are in their standard state, meaning these guys are what they would be under room conditions. Butane in your room would be a gas. Oxygen in your room is a gas. Carbon dioxide in your room is a gas. Water in your room is a liquid. Okay, so what is the sign of delta H and why? Let's talk about that first. What's delta H? Combustion reactions. Delta H is always what? Oops. Negative. Okay. So if delta H is negative, why? It's because all combustion reactions, for the sake of our class, are exothermic. All combustion reactions release or lose heat. So if a reaction is exothermic, the reaction profile looks like this, right? So it says, how does the total bond energy of the reactants compare to the products? Well, more energy is released during the formation of bonds than was required to put in to break the bonds. Okay, so the bond energy of the reactants is higher and the bond energy of the products is lower. All right. So let's look at this multiple choice equation or reaction. MCQ meaning no calculator, but this is definitely conceptual. It says, what can you conclude about the relative strength of the bond energies of reactants and products? So you look at this reaction and then you look at the delta H, and the delta H is negative, which means it tells you it's exothermic. Now, answer option B, you don't know how to do yet, and I'm going to tell you it's fine because it's wrong. So please take a second and read all of these and see which one of these is associated with the reaction being exothermic in terms of bond energy. And sorry, third period, I went too fast and sorry. Oh gosh, another Murphy moment. You'll have to put on my ticker because I think I told you it was C and I read it too fast. It's not C. What is it? It is A. The bond energy of the reactants is greater than the bond energy of products because according to the sign of delta H, more energy is released from reactant bonds than is put in when product bonds are formed. Whoa. No. Blah, blah, blah. I'm going back to C. A bunch of energy is released in the formation of new bonds than it took to break the original bonds. Sorry, second period. Oh man, this is major Murphy moment today. Major Murphy moment. Sorry, second period. Okay. All right. So here we go. We're going to actually do calculations now. So you go, okay, we have all these ways to calculate delta H. So we have Hess's law the long way, Hess's law the shortcut way, which is products minus reactants. But to do the products minus reactants, you need enthalpy of formation values. If you look at this chart, these are bond enthalpies. So what I need you to do is when you see bond enthalpies, I need your brain to go, okay, well then if it's bond enthalpies, delta H equals bonds broken minus bonds formed. Okay, now the tricky part of this at this point in the year is you don't know how to draw compounds yet. You will before winter break, but you don't know right now, which means for now I will draw them for you and all you have to do is just correctly plug in the numbers. So we're going to do the combustion of methane gas using bond enthalpy. So let's write out the reaction. So you guys can write out the reaction for the combustion of methane and then I will draw the molecules for you. So methane combusts to make carbon dioxide and water. I'm going to actually put this down here. All right, and so you need a 2 here and a 2 here. Now, I'm going to draw these for you, but you should draw them with me. So you don't know how to draw. These are called Lewis structures. You will know how to draw them soon, but you don't know yet, okay? So there's methane. There's a drawing of it. And the reason that the drawings matter because we have to look at bonds. That's what bond enthalpies are, right? The energy that's stored in the chemical bonds. So I'll give you a second to draw these.
Stop jumping away.
All right. Now, don't forget your coefficients. Oops, I'll put a plus here. So there's 2 of these and 2 of these. Now remember, this is bonds broken minus bonds formed. Remember, in chemistry, you break bonds of reactants to form new bonds as your products. That's like the point of a chemical reaction. So you go, okay, bonds broken minus bonds formed. So you look at this and you go, okay, methane. This is a, change the color, carbon-hydrogen bond. So you look back over here and you go, okay, the energy stored in a carbon-hydrogen bond is 413 kilojoules per mole. So, let's see, 413. But there's 1, 2, 3, 4 of those bonds. So you have to multiply it by 4. Plus, I have oxygen, oxygen double bond. So you go back here, that says oxygen, oxygen is 495. So you say 495. But there's 2 of these oxygen, oxygen molecules. It'd be like me drawing it twice. That's what the coefficient means. There's 2 of them. So there's 2 oxygen, oxygen double bonds. So you have to multiply this by 2. So this is bonds broken. Minus. So now I'm going to form bonds. This is a carbon-oxygen double bond. So you go back over here. Carbon-oxygen double bond is 799. So 799. But there's 2 of them. So you have to multiply by 2. Plus, this is an oxygen-hydrogen bond. So 467. So you say 467. Now be very careful. There are 2 oxygen-hydrogen bonds in a water molecule, just one water molecule. But I have 2 water molecules. So it would be like me drawing this water molecule twice. So technically there's 1, 2, 3, 4 oxygen hydrogens we have to account for. So bonds broken minus bonds formed. That is what delta H of combustion is. And I say combustion because this is a combustion reaction. I could have just as easily just called it delta H or delta H of a reaction, okay? So I'm going to give you a second to calculate it out. The number is, I think it's, yeah, -824. Oops. But I'm going to give you a second to calculate it out. So it's -824 kilojoules per mole. Look at negative. Combustion reactions are exothermic, so the sign at least makes sense. But I'll give you a second because I need you to practice with your calculators. All right, so this is another just practice problem. Again, all of these bond enthalpies are here. So you were calculating delta H using bond enthalpies. So again, when you see this, you want to think to yourself, okay, bonds broken minus bonds formed. Now I have the reaction. You know, I know you can't draw it yet, so I'm going to draw it for you. So let's take a second for you guys to be able to draw all these. So I'll do them. So here's CH4, methane. Cl2, those are chlorines, and F2, bonds broken. So this is our bonds broken minus, so bonds formed is this guy. These dots I'm drawing are called lone pairs. I don't need you to know what they are right now, but you will know what they are soon. They aren't relevant in terms of what we're doing right now. Oh, shoot, that's not what that is. Oh my gosh. These should be fluorines. And then I'm going to go ahead and add my coefficients. So I think that this was a 2, this was a 2, this was a 2, and this was a 2. You can correct me if I'm wrong. So this is bonds formed. All right, so here we go. At this point, it's just plug and chug. So if you can count, you can do this. So again, on a test or anything for right now, these will be drawn for you. So you just have to use the correct numbers with the correct coefficients. So look at carbon hydrogen is 412. And there's 1, 2, 3, 4 of them. 412. Plus chlorine, chlorine. Chlorine, chlorine is 239. And there's 2 of these guys, so times 2. Plus fluorine, fluorine. Fluorine, fluorine is 154, and there are 2 of them. So this is my bonds broken. So minus, so all these bonds being formed. So carbon, chlorine. Carbon, chlorine, let's see, 339. Oops. There's 1, 2 of them. Plus, there's also 2 carbon fluorine bonds. Plus HCl, 427. Now, remember, there's 2 of these guys. It would be like me drawing this twice, which means there's 2 HCl bonds plus HF. 565, and again, there's 2 of those, so you multiply by 2. So there's so many numbers. So these are bonds formed. These are products. So bonds broken minus bonds formed. Again, there's so many numbers. I highly suggest calculating this number, writing it out, calculating this number, writing it out, and then you can subtract them. I'm going to give about a minute or so, a minute and a half, for you guys to practice with your calculator for this. So the question I got was, do you multiply these bond enthalpies or bond energies by the coefficient or by the number of bonds? And again, the answer is both. You have to account for both. So for example, now again, this is not true. If I were to have 2 methane molecules, each methane has 4 bonds. But if I had to draw it twice, which is really what the 2 out front means, that is a total of 1, 2, 3, 4, 5, 6, 7, 8. So you have to account for the number of bonds within the molecule as well as how many of the molecules you have. Very, very good question. Both you have to account for. All right. negative 1198. I think that's what, sorry, I didn't go back. That's it. So it should be negative 1198 kilojoules per mole, meaning this reaction is exothermic and releases this much energy or heat per mole. All right. So just like when we were doing enthalpy of formation values where we were calculating delta H, sometimes you can be given delta H instead. So like the last two problems, we were calculating delta H. So in this type of problem, we are given delta H, and instead of calculating it, we want to find one of the bond enthalpies instead. So it's just a different algebraic manipulation. So again, when you see like the word bond enthalpies, or you see a data table that says average bond enthalpy, I need your brain to go bonds broken minus bonds formed. All right, so again, I'm gonna have to draw these. So hydrogen looks like this, plus oxygen looks like this. So go ahead and draw these down with me. Sorry, I ran out of room. Makes water, which looks like this. And then I'm going to do my coefficients. Okay, so remember delta H for this is bonds broken minus bonds formed. Okay, so bonds broken, that's these guys, minus bonds formed, that's these guys. Now they gave you delta H, so I'm going to go back. So negative 571.6. So we actually have that number. So we have this number. So negative 571, actually I'm going to do this up here because we're going to have to do some rearranging. Negative 571.6 equals, so bonds broken. Now, I don't know the HH bond. That's what I'm trying to find. So I'm just going to you could rewrite it as X or whatever. I'm just going to draw it as an HH, okay? I don't know. Your job is to find this guy. Plus an oxygen double bond, which is given right here, 495. Bonds broken minus bonds formed. So now I have an oxygen hydrogen and an oxygen hydrogen. That's two of them, but there's two water molecules. Again, that would be like that coefficient of 2 means I have 2 water molecules. So it'd be like me drawing water twice. 1, 2, 3, 4. So there's 4 oxygen hydrogen bonds. 4, 6, 7. Okay, so let's rearrange. So what's 4 times 4, 6, 7? So this is this minus, and then this number is 1868. That's what this number is right here. So, right, this is this minus this. So I'm going to add this to the other side. Right, algebra. So 1868 plus 571.6 negative 571.6. Oh, why does this keep doing that? So this ends up being, sorry, I'm going to do it down here. 1296.4, 0.4 equals 2 hydrogen molecules and then the oxygen, so 495. So now I'm going to subtract 495 from both sides, right? All I'm trying to do is just isolate. So this ends up being, sorry, I got to do it up here. Sorry, guys. 801.4 equals 2 of the hydrogen molecules. Now, to get the hydrogen-hydrogen bond enthalpy, you have to get rid of this too. Okay, so divided by 2, and that bond enthalpy ends up being 400.7. So like if I were to complete my chart, a hydrogen bond is 400.7 kilojoules per mole based on this data. Questions? All right. Okay, so calorimetry is just this fancy word for doing chemical reactions that involve heat, either absorbing heat or releasing heat. And a calorimeter is just a fancy word for some sort of tool or device that's considered to be insulated, right? Because when we do reactions, we want to kind of assume that everything we're measuring isn't being like lost to the room or lost to the device. So in our class, when we do labs in person, we often use this, styrofoam coffee cups because they're super good at not absorbing heat or releasing heat. So we can kind of get a really accurate measurement of like temperature changes that might happen. These are just like fancy words for, right, like doing reactions or processes that involve heat exchange, either absorbing heat or releasing heat. All right. So this is actually what we're going to end with today, is this concept. And you've actually already done this before. You just have not ever had it called calorimetry before. So it says, what is the delta H in kilojoules per mole of sodium hydroxide? And then they're going to dissolve sodium hydroxide in water. And the temperature changes, meaning the dissolution of sodium hydroxide is an exothermic process. How do I know it's exothermic? Well, the reaction gets hot. So look at, pretty much you're taking sodium hydroxide, solid, you're dumping it in water, and what happens? It becomes sodium ion and hydroxide ion, and a bunch of energy is released. That's why it gets hot, okay? It heats up. So sometimes dissolving involves heat exchange or heat changes. Some dissolving processes are endothermic. So we'll talk a little bit about that later. So we're going to assume that the container that you do this process in doesn't absorb heat. Like you don't lose heat to the surroundings. It doesn't leave into the room. The coffee cup, which we're doing it in, this styrofoam coffee cup, doesn't take in any heat. I mean, these are lies, like they do, but it's just not a lot, so we're not going to account for it, okay? And then, so you go, okay, I have all these different ways so far in this chapter to calculate delta H. So which way am I going to do? So let's go through all the ways we know. We just learned delta H using bond enthalpies. So typing yes or no, are we going to use bond enthalpies? Do you see bond enthalpies anywhere to do bonds broken minus bonds formed to calculate delta H? No. Good job. Negative. Okay. How about products minus, delta H is products minus reactants. So when we do products minus reactants, those involve enthalpy of formation values. Do you see a bunch of enthalpy of formation values of compounds? No. Okay, so that's not it either. So you go, okay, so those two are out. Hess's law of the long way, which where you have like a couple reactions to make the overall reaction. Do you see any of those anywhere? Nope. So Andy said, maybe we use MCAT. What do you think? Do I see a temperature change? Do I see a mass? Do I see a specific heat? Ooh, okay. MCAT. But now here's where you have to be careful. You have to remember, that when you're measuring the temperature of a reaction in a lab with a thermometer, you're always measuring the surroundings. So in this instance, we're measuring the surroundings, aka the solution. Okay, you could also call it surroundings. Okay, And the surroundings are obviously gaining heat, right? It got hotter. But that's because the process is losing heat. So the system, or we could call this sodium hydroxide, because sodium hydroxide dissolving is the system, is losing heat. Now, we can never get inside the molecules of the sodium hydroxide. We can only measure the temperature of the surrounding. So Andy suggested MCAT for the solution. Does the solution get hot? Yes. Does it change temperature? Yes. Temperature change. Okay, that's this guy. So mass of the solution, specific heat of the solution, delta T of the solution. And this guy's going to be gaining. Now, this is negative Q. Now, do they give you MCAT for Q? Do they give you delta T for the sodium hydroxide or the system? So this is what's harder. I guess my question is, what is the Q of the system? I'm telling you it's not MCAT. They don't give you MCAT of the system. They do give you mass, sure, but they don't give you anything else. So what Q do we use? This is the hard part. What Q do we use? What's the other Q we know? Anybody? NH. Thank you, Micah. So this will be the moles of the sodium hydroxide and then the enthalpy. Okay, so again, this is plug and chug though. All you have to do is rearrange. So minus, now what's the moles? Well, the moles are going to belong to the sodium hydroxide. Well, why? The sodium hydroxide being added to the water is what's causing the temperature change. If you didn't add the sodium hydroxide, there would be no temperature change. So it's the addition of the sodium hydroxide that is producing this heat. So this is moles of your sodium hydroxide. So the sodium hydroxide grams was 10. And if you didn't know, sodium hydroxide is 40 grams per mole. So 10 divided by 4 is 1/4, which is 0.25 moles, times enthalpy. Now, this is what we're solving for, right? Equals, so NH equals, what's the mass of the solution? Ooh, what is the mass of the solution? Is it 200? Anybody? Well, what's in the solution? Water and sodium hydroxide, right? Both things. So what's the mass of the solution? 210. The combination of both of them, the sodium hydroxide and the water, make up the entire solution. And they gave you the specific heat of the solution, 4.184 joules per gram Celsius. And then the temperature change is final temperature, 24.5, minus initial temperature, 22. So that's what, 2.5 temperature change? Okay. So let's see, units. Grams, cancel, Celsius, cancels. Now, to get this by itself, I need to divide by 0.25 moles. Okay. And then I need to move the negative sign over. So negative, whatever this comes out to be. Now, be careful. They asked, I'm pretty sure the problem asked for it in kilojoules per mole. Kilojoules per mole, and right now we're in joules. So whatever you get, you have to divide by 1,000 because this answer comes out to be in joules per mole. So whatever answer you get, divide by 1,000, and you should get, I think I have the answer in there, negative 8.78. A couple of kids got negative 8.79. Okay, negative 8.77, fine. All right, so This process is exothermic. Some heat is released by dissolving sodium hydroxide in water. This is actually true. Sodium hydroxide is a base, and whenever I make solutions with it, the container gets actually really hot. Any questions before we move on? All right, let's try another one. All right, so a student is mixing hydrochloric acid and sodium hydroxide. So this is an acid-base reaction, aka neutralization. So I'm gonna just write it out. So HCl reacting with sodium hydroxide makes sodium chloride and water, salt, acid, base, salt, water. Everything is 1 to 1 to 1. So boring. Well, nice, but boring. Okay. So they give you a volume and a molarity of hydrochloric acid and a volume and a molarity of sodium hydroxide. Before we go any further, when you see these numbers, volume and molarity, I need your brain to do something. I need you to know what they're giving you. I realize it's volume and molarity, but really what are they trying to give you with volume and molarity? Moles. Okay, molarity times volume is moles. And again, the volume has to be in liters. Very, very good. So they're giving you moles, meaning you have the moles of the HCl and you have moles of sodium hydroxide. Meaning if you have moles of both reactants, it's also known as a what kind of problem? If you have amounts of both reactants, it is a limiting reactant problem. Very good. Okay, and you go, well, what does this have to do with heat or calorimetry? What does this have to do with heat? Well, you've got to think about it. When a reactant runs out, the reaction stops. So not only do you no longer make products, but if there's any sort of heat involved, like heat being absorbed or heat being released, that also stops. So the limiting reactant truly determines everything about the reaction. It determines excess, it determines products, it also determines heat, okay? So look, they're using a coffee cup calorimeter because styrofoam cups are great insulators, and the reaction causes an increase in temperature, meaning it gets hot, meaning this is an exothermic reaction, okay? All neutralization reactions are exothermic. They produce heat, okay? And so you go, okay, calculate the enthalpy change. Enthalpy means H, change means delta. So we're calculating delta H of the reaction, so delta H of the reaction, okay? And kilojoules per mole, and then they specifically tell you for HCl, okay? And we're gonna pretend that the coffee cup doesn't absorb or lose heat, and then they give you a bunch of other information. The total volume of the solution is 100 milliliters, right? If you take 50 and you add 50, that's a total volume of 100. And its density is 1 gram per milliliter. Why do they give you this piece of information? Why do they give you density? If you know the volume and you know the density, what can you find out about the solution? It's what? So volume and density should get you grams. And then, true, you could get moles if you knew the molar mass of the solution. But we want grams, right? Why do we want grams? Is there an equation that has grams in it? Remember density? So density is mass over volume. So if you have density and you have volume, you can get mass. Why would we need mass? MCAT. Beautiful. Okay, so I'm just trying to help you like sort through the problem and why they're giving you certain things. So you go, okay, MCAT, but you got to be careful here because you got to remember that you're always measuring the surroundings. So the surroundings are going to gain heat, which is the solution, okay? When we put our thermometer in there, we're measuring the surroundings or the solution, which means this reaction is losing heat. I know it's kind of tricky, but you can't get inside a chemical reaction. Even though you put your thermometer in it, you are always measuring the surroundings. And our surroundings are our solution that's formed from the neutralization reaction. All right? So this is just like the last one. So the solution changes temperature. It gets hotter, right? Well, a change in temperature for Q is MCAT, mass of solution, specific heat of the solution, delta T of the solution. Oops. Now, the reaction loses heat, but there's no temperature change associated with it. So we do NH. Now, we're trying to find H. Again, the enthalpy of the reaction. All right, so let's plug. Who did they say they want the H per mole of? Who? They said a specific substance, right? They said HCl. So guess who the moles belongs to? HCl. And I'm going to come back to this in a minute. So how do you get moles? Well, you take molarity and you multiply by volume in liters. So it's 1 molar, and then it was 50 milliliters, which is 0.05 liters, right? So 1 times 0.05 is 0.05 moles, so minus, and then 0.05 moles times H equals, what's the mass of the solution? Well, if you have 100 milliliters and the density is 1 gram per 1 milliliter, you have 100 grams. And they tell you the specific heat of the solution is 4.18 joules per gram, and then they call it Kelvin. I'm gonna just as easily call it Celsius because I'm gonna plug Celsius in. Remember that Kelvin and Celsius are interchangeable only in this chapter. And then the temperature change of the solution. So it goes from 21 degrees Celsius to 27.5 degrees Celsius. So 27.5 final temperature minus 21 initial temperature is 6.5. Okay, so look at Celsius cancel, gram cancel. All right, divide by 0.05 moles, divide by 0.05 moles. And then remember, you got to move that negative sign over. So I'm going to put the negative out in front of here. So you end up with joules per mole. Now they ask for you for it in kilojoules per mole. So you'll have to end up dividing by 1,000 to get it in kilojoules per mole. And if I'm not mistaken, I think the number was negative 54 kilojoules per mole. And it's of HCl, right? Or of the reaction. I guess it doesn't matter. Specifically, it was HCl because they asked for HCl, and I'm going to come back to this in a second, but I want to give you a second to calculate. Everybody pay very, very close attention to what I'm about to say, okay? I know that the problem specifically requested per moles of HCl. However, I don't have to request that. I don't have to give you that information. So you go, okay, well, who would I do the moles of if it didn't say HCl? Anybody know the answer? Who should this belong to? Always, if this is the type of problem you get. The moles should always belong to who? Anybody? Guess. It's okay if you guess and you get it wrong. Just try. Who determines the enthalpy or heat of a reaction? What kind of substance? Yes, Carissa, awesome. The limiting reactant determines everything. So if they don't tell you in this problem and they say calculate the kilojoules per mole, it is per mole of the limiting reactant. So the question is why did they use the HCl? Well, they could have easily used the NaOH. Here's why. You have the same number of moles of HCl and NaOH, and they're in a 1-to-1 ratio. So it didn't matter who you used. It didn't matter if you used HCl or NaOH. However, be very careful. You never combine them. It's only per one of the limiting reactants. There's only one limiting reactant. So if they're in perfect stoichiometric proportions, just pick one. If they are not, you will always pick the limiting reactant moles because the limiting reactant determines every single thing about the reaction, including heat. Okay? So always use the limiting reactant for your moles if you have a problem like this. Okay? And again, they used HCl because it didn't matter, because both the molarity, this was the molarity and the volume of the sodium hydroxide also. So your moles were the same. The reaction was a 1-to-1 ratio. It did not matter who you used. So here's where we're finishing for in class. This is this was on the multiple choice test, I think like 2 or 3 years ago. So this is a chemical reaction. Notice it's not an acid-base reaction. However, it's a precipitation reaction, right? You take 2 aqueous solutions and you get a solid out of it. And they're mixing 50 milliliters of 0.1 molar silver nitrate, so that's this guy, and 50 milliliters of 1 molar, or 0.1 molar sodium chloride. So what are they telling you with these numbers? The 50 milliliters and 0.1 and the 50 milliliters and the 0.1. What are they giving you in essence? Moles, right? Molarity and volume gets you moles. Molarity times volume is moles. And remember, this has to be in liters. Okay? And here's the balanced reaction. Everything is 1-to-1 to 1. And they do a coffee cup calorimeter, which just means an insulated styrofoam cup. Which of the following is the enthalpy change? So delta change H, enthalpy, of the reaction. So I could just write reaction. And I tell you the final temperature of the mixture is 21, and it was at 20. So you're going to assume that the total mass of the mixture is 100 grams. Well, why is that? Well, 50 plus 50 is 100. The density is probably 1 gram per milliliters. And the specific heat is 4.2. They give you this abbreviated number because you're technically not supposed to be using a calculator on these. So it has to be math that can be done fairly easily without a calculator. So how do we set this up? The solution, or whatever, the surroundings are gaining heat, right? Because they're getting hot. But the reaction is losing heat. Remember, we're always in the solution. We're always measuring the solution. So if it's getting hotter, it's because the reaction is losing the heat to the solution, aka the surroundings.
Oh, okay. That's fine.
Now, what equations do we use? Well, if the solution is changing temperature, the equation for Q with temperature is MCAT. So M of the solution, C of the solution, and delta T of the solution. Now, what is Q of the reaction? Anybody? So opposite, just like we've been doing. Moles, H, right? And then we're trying to find H. That's what it says. They want the enthalpy change. Now, I'm going to off the bat move the negative sign over, okay? So this negative is going to come to the other side. And then I'll divide by mole. So I'll just leave all the variables in and then plug in. Okay? So let's plug in numbers. H is, what's the mass of the solution? They told you it was 100 grams. And the C of the solution is 4.2. And they did this, did they give you, it doesn't matter. You could put Celsius or Kelvin. Yeah, they put Celsius. They did this because you don't get a calculator, so they want you to just do your best with conceptual math. And the delta T of the solution. Well, if you look back at the problem, the final temperature of the solution was 21, and the initial temperature was 20, so that's only a difference of 1 degree Celsius, which is, right, that's going to be nice for us. So Celsius, cancel, gram, cancel. And then, divide by mole. So my question to you is mole of what? Mole of what? You get to pick one, right? Either one of them. Now, not both of them, but pick one. And the reason you get to pick one is because this is the mole of your limiting reactant. And if you look back at the problem, the reactants are in a 1-to-1 ratio, and you have the same exact molarity and volume for both reactants, which means you have the same exact number of moles of both reactants. So molarity times volume is moles. So you go, okay. I'm going to just do it right here. Molarity and times volume is moles. The molarity is 0.1. So I'll write it as 0.1 moles per liter times, now 50 milliliters, I have to convert to liters, so I divide by 1,000, so that's 0.05 liters. So 0.1 and 0.05 is 0.005 moles. Okay, now I'm going to rewrite this, right? Because technically you're not supposed to have a calculator. So I'm going to rewrite this like this. 4.2 joules per 5/1000 moles, right? This is this number in fraction. And the reason I did that is because I know that now I can do this. 4.2 joules times 1,000/5 moles. Okay, and then I go, oh, all of my answers are in kilojoules. So, sorry, I'm kind of running out of room. There are 1,000 joules in 1 kilojoule. So these thousands go away, and I end up with I'm sorry, my bad. Why did I say 4.2? 100 times 4.2 is not 4.2. It's 420, sorry. 420. Right, you move the decimal over 2 spots for that 100. 420. So then you go, okay, well my thousands cancel out to turn it to kilojoules. So really you have 420/5. So here's what you should do without a calculator. You go, okay, what is the closest whole number that I know to, that I can divide by 5? So like 40, right? 40 divided by 5 is 8, right? But this is 420, so it's like 400 divided by 5. 40 divided by 5 is 8, but there's an extra 0, so I'd put 80, right? But it isn't 400, it's 420, so it's going to be a number a little bit bigger than 80, and then do not forget the negative sign. So if you look on here, our answer is going to be A, negative 84, so a little bit more, right? Because the number is really 420 and not 400 kilojoules per mole. Energy released. This process is exothermic. All right, I'm finished here for in-class time. I will continue the notes in a little bit. I probably won't post them till a lot later this afternoon, but this is what I'm finishing with today. The rest of notes is not that it's not important, but I'm gonna just kind of go over it briefly. It's very similar to what we've been doing. It's heat capacity instead of specific heat capacity, where we actually consider that the calorimeter or the tool that we're using can change temperature, because they really can. And that is what ends the notes, but I will do that outside of this class time. But I will post everything in the notes so you can watch them on your own.